Our first speaker today is I'm very pleased to have her on. It's Dr. Emily Fairfax, who's an assistant professor of physical geography in the Department of Geography, Environment, and Society at the University of Minnesota, Twin Cities. She is also affiliated with St. Anthony Falls Laboratory at the University of Minnesota. Her current research focuses on the ecohydrology of riparian areas, particularly those that have been impacted by beaver damming. Dr. Fairfax recently located back to Minnesota, and we're delighted to have her in the Midwest. Her work around fire and hydrology is very significant, and we're delighted to have you here this morning. Thank you, Emily.
Awesome. Thank you for the introduction. So let me go ahead and get my slides up for everybody to see. So I'm going to be talking to you today about beavers and floods and droughts and more. And really the take-home message of my presentation is about how beavers can help us build landscape scale climate resilience. So climate is changing. I hopefully don't need to convince anybody on this call of that, but I want to point out that what used to feel very normal in Minnesota, in Wisconsin, in Iowa, Illinois, Indiana, Missouri, Oklahoma, and so on, isn't really what we're feeling anymore. Normal is changing. Every single decade for the last century has been hotter than the last, and we're not showing any signs of slowing down. This is a trend that has been going on, is still going on, and we're already feeling the impacts of this today. Specifically here in the upper Midwest and the Great Lakes region more broadly, there are some big changes coming with climate change and some big changes that have already arrived. We have seen in the last few decades a temperature rise of 2.3 degrees Fahrenheit on average. Our frost-free season has increased by 16 days. We have 14% more total precipitation, and our heavy precip events are up 35%. And I want to be very clear, this is the climate change effects that we are already feeling. This has already happened. There's going to be more past this. It's going to get hotter. The frost-free season is going to get longer. We're going to get even more rain. I know at my house, we have already gotten more than the entire year's worth of rain already, and there's still several months left in the year. And most of that rain has been coming in these huge precipitation events. And this is a challenge for us. Having these wetter winters, especially when it's coming as rain, not snow, is new. Having drier summers, even though it's more precip total, that precip's not coming necessarily when we need it. That's new. And having it be so much hotter and having these storms have so much more power is new. So there's a lot for us to think about and a lot for us to deal with. And probably a lot of you have quite viscerally felt this past year. I, as Bob said, just moved back to the Midwest about a year ago, and I had been in California. I had become very soft to winter temperatures, and I moved back and I was like, all right, I'm ready for Minnesota winter again. I'm ready to feel that -40. And then the fall kept going on. It was September, October, November, and into December, and it was warm. And I looked at it and it was abnormally warm. It was the 7th straight warmest than average month in November. I was like, all right, well, easy fall, but winter will be serious. That'll be when it's cold. And then it wasn't. It was one of the hottest winters we've ever had on record. I was like, okay, well, winter's done now. We'll have a pretty normal spring and fall and summer and all that'll be fine. And yet it hasn't been. It has been extraordinarily rainy. We have had extreme storm events. We have had severe heat waves. And this is not the Minnesota that I lived in 10 years ago. And I'm sure this is not the Minnesota or the Midwest that a lot of you have lived in for decades and decades. So this climate change is very real, and it's not really creeping up on us anymore. It's kind of hitting us in the face. Interestingly, another climate problem that we haven't had to think about a lot, but that is becoming our problem, is fire. And although you wouldn't know it now this summer with all this rain, during the spring, we were one of the only places in the United States that had an elevated fire risk. And it's because we had come off of this hot winter and having weird rain that wasn't staying on the landscape the way snow would, it put us in this really precarious position for fire. So this is all a lot of changes, and we need to stay ahead of the curve on this because there's a lot of things that we care about here in the Midwest: our forests, our waters, our lands, our prairies. We don't want to see them succumb to the challenges of climate change. So what do? It's obvious that we need to be building more climate resilient landscapes. We can't keep watching forests go up in smoke. We can't keep watching our reservoirs drop and our lake levels drop and the boat ramps all get exposed. And we can't keep watching our cities and our towns go underneath floodwaters and have the banks ripped away and houses fall into the rivers. That's not acceptable. That's not a future we want. And it feels natural to us as people to think, okay, well, we need to engineer something better. We are incredibly smart as a species. We have come up with so many creative ways to deal with the challenges that nature deals us. So we need to engineer our way out of this too, which I say is probably true, but we don't need to do all that engineering by ourselves. And as you may have guessed from the theme of this summit, I am talking about nature's engineers, which is the beaver. And I want to point out to you all the ways that, yes, we do need to engineer more climate resilient landscapes, but that engineering does not all have to be done by ourselves. We can partner with nature's engineers to work towards the same goals in a faster, more efficient, and more effective way. Now you might be thinking, okay, beavers, I do know what those are, and climate change, I do know what that is. But seeing these two concepts in a sentence together is maybe not as familiar. I'm the first to admit that beavers and climate change is not the same thing as peanut butter and jelly. It's not salt and pepper. These aren't typical conversation items, or at least they haven't been until very recently. But beavers have a lot to do with climate change. They are nature's engineers. And what you're looking at right now is a pretty classic beaver dam landscape. This one was taken, this photo was up in the Boundary Waters, taken a couple of years ago. And it's what you would see in most beaver wetlands. You've got a variety of tree species here. There's conifers, there's deciduous trees, there's all sorts of different weeds and reeds and wetland plants. You have flowing water, you have still water, you have a beaver dam. This is a complex landscape. This is a mosaic of habitats. And this is what a lot of the upper Midwest and the lower Midwest and all of the general middle of the country used to look like for hundreds and hundreds, thousands and millions of years. But today, this is not what most of our waterways look like. In fact, we tend to see something a little bit more like this. So this drawing in the bottom left is a simplified stream. It is degraded. We've seen it cut away from the surrounding landscape. It's no longer interacting with the floodplain as it used to. And as a result, it's not able to support the same kind of ecosystem. We don't get to see that complexity. It becomes very simple. And when our streams and rivers become simple like this, they lose their ability to be resilient. We struggle with these. They've gotten this way for a number of reasons, from overgrazing by cattle and other ungulates to draining for housing developments and things like that, to even some restoration projects from decades past that aren't working the way that they used to or have stopped to be as functional as intended. And this is a challenge for us, but it's not a challenge for beavers. So beavers see a stream like this and they are like, hot damn, perfect opportunity for me. I'm going to build a dam. And that beaver dam, I want to be very clear, is a leaky structure. Water is constantly flowing over these, under these, around these, through these. It does not stop the water. But what a beaver dam does do is slow the water down. And it gives it time on the landscape to seep out into the soil. It elevates that water back up towards the floodplain, causing a reconnection, which lets it spread out just a little bit more. And you begin to build back up this riparian or streamside ecosystem. And the beaver's not going to stop there. Busy as a beaver is a phrase for a real reason. They are not done when it's just this one little dinky dam. They want to expand it. So beavers are going to make that dam longer. They're going to make it taller. They're going to try to make it stronger. They want more aquatic area for themselves. Beavers are a semi-aquatic rodent, meaning that they live both on land and in water. And I wish that you all were in person with me because I love to actually see hands on this question. I want you to think, how many of you have actually seen a beaver in real life? Just ponder that for a second. And now think if you've seen them walking on the land, not swimming. A lot of us have seen them swimming, but actually walking. And I bring this up because beavers on land are extraordinarily vulnerable. They are like a great big waddling chicken nugget. Any predator would be happy to have them as a snack. And here in the Midwest, we have some predators for them. And they know this, evolution taught them this. When they're on land, it's bad news. So all of this dam construction, all of this expansion of aquatic area is actually just to increase their safety. For every ounce awkward a beaver is on land, they are 5 times as skilled and agile and graceful in the water. This is an animal that can hold its breath for 15 minutes. They can outswim essentially any predator, and they are in control when they're in the water. So beaver's doing all this extra construction. It's making bigger ponds because it wants to be safe, but that rapidly increases the amount of wetland habitat available, not just for the beaver, but for all of these other organisms that might want to visit it as well. And so, yes, we've established now beavers are awkward, but what do they do when they have to leave their ponds? They can't spend every minute of every day in the water. They need to go get their food, which is bark on trees or new plants like reeds and weeds. They need to get building materials. They need to cut down material to build more dams, to build their lodges. What are they doing? Are they just hoofing it out on dry land, taking that risk into their little paws? No, they are digging canals. And this is one of the things beavers do that a lot of people don't actually realize. The beaver dam is this very obvious structure and it's in your face and you're like, wow, the beaver has changed a lot with that dam. But these canals that they dig, they're like little micro streams that radiate out from the beaver's home pond across valley bottoms, across floodplains. They can be tens to hundreds of meters long. And each one is a conduit for water. It's a conduit for beavers. It's a conduit for nutrients. And it's spreading out and it's radiating. And that vastly increases the beaver's area of influence. Importantly for the beaver, it's like a little highway system for them. So if they're out trying to chew on a tree or get some more food and they sense a predator or get spooked, they can slap their tails, jump into a canal and swim home. That's their transit system. But more importantly, it is the water's transit system. And now just to get our terms straight, if you were in a beaver pond, you would see something kind of like this. We've got that beaver dam on the left-hand side. That is a structure that they build but do not live in. It is to hold back water. It is to increase aquatic area. Beaver lodge, this is a dome-shaped structure. I've also called them or heard them called beaver huts and houses up here. This is what they're actually spending their time in. They pile up sticks and mud and stones. They chew little rooms out inside for themselves and sometimes for other critters too. You can find muskrats and mice and snakes and frogs and things taking up residence more or less with the beaver's permission inside their lodge. You see the ponded area, you see the beavers in the background on the land looking round and awkward, chewing on trees, got the beaver in the water, swimming, looking in control, very graceful. This is accurate. This is a pretty good representation of a beaver wetland, but it's also very simplified because beavers aren't just building one dam or a couple canals. And the scale of this, the dam to the lodge, it's a little bit misleading. This is a classic portion of a beaver wetland that you might find here in the Midwest. So we've got the beaver lodge, a round dark blob in the sort of center left of this image. And if you really squint at my screen and maybe turn up your brightness, you can see a little tiny pale dot on that lodge. That is one of my research assistants. So that is a human for scale on the lodge. And then we've got these two vast beaver dams sweeping across the landscape. And what I really want you to notice here is that they are connected hydrologically, both ponds. The water is flowing around, it is flowing over, under, through these beaver dams. This is not the case of flow obstruction, like when we put in concrete dams. This is beavers building a highly complex wetland ecosystem, which dams are part of, but also canals, which leads to just a vast amount of aquatic connectivity. And it's through all of that complexity and connectivity that beavers are actually able to act as our agents of natural climate mitigation and adaptation. So complexity builds resilience, and I'm going to show you exactly what I mean by that. And it all starts with floods. So here we have a more simplified stream. It doesn't have a lot of channels. There's not much debris in it. There's not a lot of stones or logs or beaver dams. The vegetation along the banks is thin, if present at all. And this is in contrast to a beaver pond, where we have the canals, we have the dams, we have more connectivity, more flow paths, and a lot more vegetation. When you have a storm event or a big snowmelt or just your annual high water, that creates a flood wave. And when flood waves are confined to too small of a channel, they have too much power. Think about this like if you turn on your garden hose and then put your thumb over part of the front of it and try to constrict the area that that water can flow through. Suddenly, instead of being a nice trickle that maybe you can drink out of, it becomes this blast that you can spray your friends with, or even sometimes, if you think about power washers, scour material off of your sidewalk with. That's what is happening here. We have too much water confined to too little space in these streams. It's not connecting to its floodplain. So instead of having a very natural conveyance of water downstream, what we have is even relatively small storm events ripping apart the waterways. They are too powerful, too erosive. It's too much water in too small of a space until it hits something like a beaver wetland. When flood waves enter these areas, there's more water, there's more area, it's deeper. The canals help route that water out onto the floodplain. It's easy for water to flow where there's already water flowing. And you get this sort of spreading out of that flood wave. It's still the same amount of water coming through. There's just a lot more space for it. And as it goes out on the floodplain, it's encountering vegetation, which is like little bristles or brushes that slow the water down even further. They can help knock some sediment out of it, knock material out of it, knock nutrients out of it, and get it onto the landscape that needs that. And the water does make its way downstream. Remember, they don't stop the water, they're just slowing it down. And so it's going to come down, but it's going to come down in a less intense way. So instead of having this large scale erosion and soil loss and scouring in our degraded systems, what we have instead is water being spread out, slowed down, and stored temporarily, stored on a number of different timescales. Some water is slowed down by a day, some water is slowed down by weeks, sometimes months. Get enough of these in a row and you can slow down by years. And that's how we do things like recharge aquifers. Now, I want to point out what this looks like in terms of some of the times when we need snow and we need water versus when we maybe don't need as much of it. So what they're doing really is slowing water down. On the x-axis, on the bottom horizontal axis of this graph, I have time. And we go from January through December, and I've color-coded different general times of the year, when we have snow accumulating, when the plants are growing and they need the most water, and then when we typically have the highest risks for things like droughts and fires. So when there's a lot of plants that are really thirsty and maybe we don't have as much rain anymore. On our y-axis, that vertical one, that's going to be stream flow, and it's measured as a volume over time. And so what you can think about is this is like how much water is coming through the stream at a given moment. I want to point out that we have flood risk year round, and this is increasing the amount of flood risk because we have more precip and because we have more heavy storm events. But we also have some very interesting floods that we're starting to grapple with, especially further north. We're seeing more and more rain on snow events. So while we do have lots of soil that can typically hold a lot of water within it, when the ground is frozen in winter, especially on those shoulder seasons, and then we get a big rainstorm, water cannot go into the soil. It has to go into surface water areas. It has to go into ponds and lakes and rivers. And if we don't have enough capacity for that, then these rain on snow events can lead to really catastrophic flooding beyond what you would expect just given the amount of precip that fell. So with that in mind, and that floods are always going to be a challenge for us year round, this is the kind of stream flow we typically see in a stream that is undammed. There's not a lot of beavers on it or none at all, and the water is just free flowing. You don't have super high stream flow usually during the winter. The water is frozen for the most part. It's in the snow, still locked up. As it melts, it goes into our streams. That's when we see the creeks start running a little bit faster. That's when the waterfalls start flowing a little bit more. It's when the river rises. And then as we go into summer, it'll taper off. Depending on how many summer storms you have, it might taper off more slowly, or it might drop off very quickly if it's a drier year. And then we don't typically have quite as much of that precipitation coming and getting into our streams as we get into late fall and then back into the snow periods. If you have beavers on these streams, instead of getting that big sharp peak, a lot of water for a short time of the year and then hardly any after that, you sort of smear it out. You have water less so in the spring, so it looks and feels like there's less water coming through in your springtime. But then as you get into late summer, you have more base flow and there's more water going through your streams because it's just taking a little bit longer to get there. It's not that it's been stopped. When you see your streams running lower in spring, the water's not gone. It's just coming in at a little bit slower pace. And so mathematically, the total amount of water that the system gets is the area under these curves. And it is pretty much the same, whether you have the beavers or not. You will see some losses in the beaver dammed streams, and that is water going back into our groundwater system, and it is water going to the plants. It is keeping them alive. It is the evapotranspiration. It is why plants are green. So it might feel like less water because it changes the delivery that we're expecting and that we're used to, but it's not less water. It's just different timing of water. And I want to point out that this concept applies to an annual high water event, sort of like I modeled out for you here, but it also applies in these short duration storm events. So if you have a really big thunderstorm, like I had last night and the night before that, you get a huge amount of rain. We got an inch of rain in about 30 minutes at my house. And that was an enormous amount of water, and you could see it flowing and looking for something to pool in. And when it gets to retention ponds, that's where it can sort of settle down and slow down and stop ripping down the streams and streets and just take a breather. And that's what beaver dams do for us during these short-term storm events too. You get a lot of runoff happening. The rainfall rate is exceeding what we can actually absorb into the soil. And so all the water rushes into the streams, hits those beaver wetlands, same thing happens. It spreads out, it slows down, and it's delivered downstream a little bit more slowly. So I wanted to give you some quick info and stats. And if you are somebody who screenshots slides, this is a great one to screenshot about floods. So this isn't just something that happens in conceptual models. There have been quite a few studies on beavers and floods. I'm highlighting a few of my favorite ones here that are illustrative of the kinds of flood wave attenuation or flood mitigation that we see. So an analysis in the UK found that 60% of a flood wave could be attenuated, and they looked at over 1,000 storm events for that. In Canada, it was determined that over 2/3 of beaver complexes were able to persist during an extreme rainstorm. And I want to point out how extreme this was. 2 meters of rain in 4 days. In American units, we're looking at like 6+ feet of rain in 2 days. That's an enormous storm. That is not like, oh, it was a big rain event like I just talked about 2 days ago. This is catastrophic, like 1,000-year type storm. And even in that, 68% of those beaver complexes were persisting. In Washington, a study found 243 cubic meters of surface water storage per 100 meters of stream length in these beaver ponds, and that 2.4 times as much more was stored underground. So they're storing this water very, very effectively. And they're raising the water table around them. And that's what creates this sort of buffered, continuously wet ecosystem, which our wetland fringes around lakes, around rivers, around streams should be. And importantly, the study also found that they were much more stable when they were near beaver ponds. They were less affected by disturbances and lack of precipitation, things like drought. So speaking of drought, I want to talk a little bit about that next. We have a stream without beavers on the left here, the stream with beavers on the right. On the left, you can see during our rainy periods, you have infiltrating precipitation. It's going into the soil. All the plant roots can reach it. In your degraded stream, there's not a super large area of influence on that shallow groundwater or soil water system. In the stream with beavers, it's a much wider area of influence from the pond. And then each of those canals is like a little micro stream along the surface. But as long as we have rainfall, as long as there's water coming in from above, it doesn't really matter to the vegetation where that water is coming from. If it's the rainwater, if it's the soil water, as long as there's water, it's happy. But as soon as we enter into a period of drought and you cut off that precipitation, and it might feel silly thinking about drought given how wet this year is, but last year was a drought. It was dry, we had fire bans, we had all sorts of issues like that. This happens here. You cut off the rainfall and all that vegetation that's grown up during your wet periods can't reach water anymore. The soil dries up. And those plants are still thirsty. And when they can't drink anything, they start to shut down and they wilt and they wither. And when they do that, you're losing that habitat that they had been providing. You're losing their ability to continue cycling carbon. You're losing all of the different ecosystem services that wetland vegetation provides. But not when there's beavers there. What we've seen in these cases is that because the beaver wetlands are so good at slowing down and storing that water during our flood periods, that when we enter into one of these drought periods, there's so much water in the soil itself that these beaver wetlands and the vegetation within them do not feel that drought. And this is something I've personally studied in the American West, and it's also something that's been studied up in Canada by some of my colleagues. So I'm going to briefly show you a little bit of my data to illustrate this point, and then give you some more quick stats on droughts. So I was really interested in this ability of beavers to buffer drought, and I figured I would look somewhere that I knew was going to be experiencing really severe droughts. And I wanted to use 3 tools: Google Earth, Landsat 8, which is a satellite, and then a model called Metric, which models evapotranspiration, and then again, Landsat 8. And what these different tools let me do was find and measure a bunch of different beaver dams, model how much evapotranspiration or water cycling was happening in this landscape, and then see how green it was, how sort of verdant were the plants, were they lush or were they sort of not that green? And the goal with this was to be able to compare vegetation health in dammed versus undammed areas during different scales of droughts. So I looked in a place in Nevada that was experiencing multiple droughts. They had a seasonal drought every single summer, it was super dry, but then they were also in the middle of this big 3-year drought. And I found a place within this study area that had an area with a lot of beavers within it, and then a portion of it that had almost no beavers within it. Other than that, they were very, very similar hydrologically, geomorphically, ecologically. The beavers were the big difference between these 2 places. I wanted to look at ET, or evapotranspiration, which is a measure of water use in the landscape. And so this could be water use from plants, so when they're doing photosynthesis, but this can also be like evaporation off of a pond surface. That can be evaporation off of concrete. You can get a really high ET signal from a puddle in your driveway evaporating. You can also get a really high ET signal from a jungle in the middle of summer doing a ton of photosynthesis. So I looked in wetter months like April. I looked in drier months like July. I looked before droughts. I looked after droughts. And I did the same thing for measures of plant greenness and DVI. I looked during wetter months. I looked during drier months. And over, what I kept seeing was that these beaver dammed areas seemed to be completely agnostic to the droughts. They were not feeling them. And when I plotted out every year's data of the drought years, which are shown here with dashed lines, and the non-drought years, which are shown in solid lines, in our beaver areas, which are blue, versus our non-beaver areas, which are yellow, what I saw was that every year in the beaver dammed areas, we saw the classic seasonal arc of evapotranspiration, which you can think of as the classic seasonal growing season arc. Your plants green up in the summer when they have lots of sun and it's warm and water, and then they green down in the fall when they stop having as much sunlight. And you expect that arc year after year after year after year. When we didn't have beavers, in the wet year, we saw a little bit of that arc. It was lower down, it was less intense, there was less water being used, less plant biomass, but it had a little seasonal arc. But in our drought years, where we didn't have beavers, we failed to have a growing season. The water, as soon as it stopped coming in April and May, those plants shut down. They did not green up. And if they did green up, it was for like a month, and then they were done. And that's not helpful. It's especially not helpful 3 years in a row. That's habitat for sensitive species. That is a place where we have carbon sequestration happening if the plants are alive and active. And what we found in this case study was that where we had beavers, there was no measurable drought effect on the ecosystem. It was completely buffered for the entire drought period. Where we did not have beavers, it was extremely sensitive to those multi-year droughts. And that persisted through the entire 3-year drought that I was looking at. It maybe could have gone on longer, but the drought ended, so I don't have data because I can't force the drought to keep going. But I'm not the only one who's seen something like this in my work. A study up in Canada found that the beaver wetlands maintained their open water surface area much better than wetlands that didn't have beavers present. So again, this is a wetland to wetland comparison. And even though you would expect both of them to be full of water, the beaver wetlands were much more able to withstand these disturbances like drought. And then a very recent study that I've worked on with a postdoc in my laboratory, she used ancient sedimentary DNA to look back in time in the greater Yellowstone ecosystem and found that beavers were continuously present even during extended droughts that lasted over 100 years. And this was correlated and collaborated with by other studies as well. So what we're seeing over and over is beavers can handle droughts, and beavers need aquatic habitat, which means their aquatic habitat can also handle droughts. And it wouldn't be a talk that I'm giving if I didn't at least touch on wildfire. And so I want to point out what happens when we let our droughts run amok and that we don't have any resistance to them, and that's fire. So this has been a problem in the American West for a long time, and it is absolutely creeping eastward. Until maybe 2020, a lot of people thought that wildfire was sort of a West Coast problem. And then 2020 megafires just absolutely erupted through the Rocky Mountain range. And now wildfire is kind of like a west of the Mississippi problem. But as we keep seeing weather change and climate change, we're seeing drying patterns change. We're seeing a lot of fire risk in places that didn't used to have as much. You just have to look a little bit north up to Ontario to see hundreds of thousands of acres burning every single year in boggy, swampy landscapes. And in some ways, it's worse when places like the Midwest have fire because we are normally much wetter and we do have a lot more biomass. There's a lot more plants here, which means there's a lot more fuel. And when things dry out, when they're not buffered against drought, that's when we see things like fire. But at least what I've seen in my research is that as long as you have beavers there doing their thing, those riverscapes are fire resistant. And this is something that's been seen in conceptual models like I've shown you, but also in actual data. These photos are from my colleague, Dr. Joe Wheaton at Utah State University. We've got the Sharps Fire back in 2018 in Idaho. On the left, the stream without beavers. On the right, stream with beavers. Pretty clear difference here in the amount of burning within the river corridor. This is something I was really interested in and went through a bunch of different fires to figure out how consistent it was and how often this kind of thing happens. And what we found was this is happening over and over and over again. I've got a couple of photos here from some fire scars I've been studying more recently. And to put numbers to it, we found that beaver dammed areas burn 3 times less intensely than places that do not have beavers within them. And I published these results and I felt really good about it. And then we started seeing wildfires get exacerbated by climate change. We started seeing megafires rip across the landscape. And these are sort of the future of fire in North America. And I wanted to know, can these beaver wetlands withstand them, even when the fires are this extreme, even when there's fire tornadoes and firestorms and hundreds of thousands of acres burning in the span of a couple of weeks? And the answer was yes, they can. In my research, what I found was that if you're outside of a river corridor during one of these massive fire events, it's about 40% chance that that area is going to be what's called fire refugia, or a patch that is not burning intensely, if at all. If you're within river corridors and stream networks, it's about 60% is fire refugia, which sounds a lot better than 40, but this is barely better than a coin flip. So if you're caught in a wildfire and you flip a coin, and that's pretty much the odds if it's going to burn or not if you're standing within the river corridor. Really different though, when we're in those beaver dammed areas, 90%-ish of them was fire refugia. They're much, much, much more consistent at creating these fireproof patches because they create drought-proof patches, because they're good at slowing down water during floods. It is a full cycle process with beavers to create climate resilience. The work they do during flood helps them during drought, which helps them during fire, which helps them again during drought and flood, and so on and so forth. It's this continuous feedback loop that makes them so stable and so climate resistant. You might be thinking, okay, I believe you, what about here? Some of this data is from the American West. We're different here in the Great Lakes and in the Midwest, and that is absolutely true. We are different here, but not necessarily as different as we think. A study that I like to point to from Ontario's Boreal Shield found that 90% of the fire-resistant wetlands up there were associated with beaver dams. And so this is places where peat is burning, this is places where bogs are burning, and even so, we are seeing that the beaver wetlands are providing climate refugia. They're providing stable habitat that is preserved, that continues to provide space and food and resources for fish and frogs and birds and mammals and beavers and everything else, even during really challenging fires. So your key info and stats on wildfire is that we see them burning 3 times less intensely where you have beavers present, and that this holds true even during our worst fires. And this holds true even during peatland and boreal fires and Midwest style fires. This is something that we need to be paying attention to if we want to be proactive instead of reactionary with our land management and climate disasters that are coming down the pipe. And if none of that motivated you, maybe dollars will. There was a great study in 2020 that went through and tried to put a dollar value on all the different ecosystem services that beavers are providing for us. And what they found was that between moderation of extreme events like floods and droughts, they didn't even consider fires in this study, greenhouse gas sequestration, water quality, water supply, hunting and fishing, biodiversity, nutrient cycling, and historical value, we see $179,000 of benefits per square mile that's engineered per year. So this is a continuous benefit to us. It's not just when the beavers first move in. Every single year, they are providing continuous monetary benefits in the amount of water purification, water storage, disaster mitigation that they can provide. So if you're thinking, now what? I'm sold, beavers are great, what's the next step? Should I start airdropping them across North America again? This is real, we did do this, not in the Midwest that I know of, but California and Idaho, both back in the day, in the 1940s and 50s, I believe, dropped beavers out of airplanes with parachutes to get them back on the land where they needed them. Is this the next step? For us, absolutely not. We do not need to be doing this, especially here. What we do need to be doing is collecting a lot better data. So one of the most interesting and also disappointing things that I found expanding my research and looking a lot more carefully at what has been done for understanding beaver impacts in the Midwest is that there's very little data. And the data that we do have, a lot of it is very old and the methods are not up to date and the research could be a lot better and a lot stronger. For example, there was a good review paper that found that when you look through the literature on beavers and fish relationships, 72% of the negative impacts that are cited don't have any data associated with them. It's just people saying things and like, oh, I think all the fish get stuck behind the beaver pond, and there's no data. It's just not backed up. And about half of the positive impacts are similar. People say things like, oh yeah, the fish love the deep pools, and there's just no data. And that's a problem. We need to have data. There's a big space for observations and anecdotes, but we need to have more data. And what that means is we need to study these systems before we go in and modify them and manage them. We need to get real temperature maps, not just single point measurements. We need to look at the effects of beavers during normal periods, but then also during those drought periods. A study out of University of Minnesota Duluth found that water temperature differences in beaver ponds wasn't particularly noticeable during the non-drought periods, but during a drought period, the beaver ponds were notably colder than other parts of the streams. And so there is sometimes this temporal difference of when do the beavers matter? We need to look at nutrient and pollutant responses, both in individual ponds, but across complexes. We need to be intentional when we do modify landscapes, when we're putting in coexistence structures, when we're doing beaver removal. Let's study that carefully so that we can know what's happening. And then finally, let's actually figure out what our historical conditions were. The Midwest is an extraordinarily modified part of the country. We have a vast amount of agriculture, we have a vast amount of development, and we have drained so many of our wetlands, and we have cut down so many of our forests. How many beavers did we used to have? How many could we have? How many should we have? Those are all different questions, and we don't have answers to any of them. So what I want you to take home from this is that beavers are very powerful when it comes to climate resilience. They can help us during droughts, floods, fires, heat, all of the above. We need to know more about who can use these, when are they useful, what are they actually doing. We are super short on data here in the Midwest. And so if you have a study idea, chances are you're going to be the first person to publish on it in this location. And we need to figure out who actually needs information. How do we work together more effectively? How do we get scientists and land managers and policymakers and NGOs all in the room together with the community members that care about beavers to make decisions that benefit us all? And I want to point out, I just wrote a review paper with my colleague Sherry Westbrook that is all about how beavers came to do this kind of work, to be mitigators of climate change. And so if you want more citations or more details on any of these topics that I touched on, that paper will be open access this fall, but it's currently early access. If you need a copy, just email me and I can send you a PDF. So I tried to save 10 minutes for questions. I only saved 5 minutes for questions, but I am happy to answer any that you all have. And if I don't get to it, I will try to respond in the chat. So thank you.
Thank you, Emily. That was a fantastic presentation, as always. We do have a few questions. One of them is, it comes from Scott Hatfield. He asks, is there a way to estimate flood mitigation potential in beaver systems, say volume of gallons? He said he's only seen a tool for constructed wetlands like stormwater detention ponds. And so that's the question. Is there a way to estimate that?
There's a few ways that you can estimate their ability to deal with flood waves. There are a number of models that take into account the amount of sort of available dam height that is typically found at beaver dams within a complex, and that can be modeled out to a surface area that is able to accommodate flood waves. You can also look at the entire floodplain, model how much water is typically stored in your soil, how much is pore space that can accept water during a flood event, and then include that in your model as all an ability that can drain water. Because those canals do get floodwater out on the floodplain, you're not just storing water in the surface water reservoirs itself, you're also storing it in the canal structures and in the soil that's available, at least during non-frozen periods. So yes, it's modelable. It's not a super easy model, but it's doable.
Okay, thank you. There's another one from Marty Garn. He asks, how do trapping policies affect programs to restore beavers on the landscape and ecosystems?
It's a great question. Trapping policies vary a lot, and the type of trapping very much matters. So we see recreational trapping and tribal trapping is not typically an issue when it comes to beaver populations. They're very responsible in my experience with not over extracting from the population. Nuisance trapping is different because that is typically around conflict areas, whether that's like a trout stream or a road. And in that case, the removal of beavers is not being distributed across the landscape. It's these like pockets of intense removal. And that can really change the ability for beavers to modify those landscapes in positive ways. And it can be at odds with conservation work that has a different goal. Say, if you're not trying to preserve a trout, you're trying to preserve a water bird, you might be head to head on whether or not you want beavers.
Okay, thank you. Andrea Knudsen, who's a professor at University of Michigan, asks us, how are beaver wetlands affect these giant bodies of water here in the Western Great Lakes? For instance, on a landscape scale, what would the effect upon the Great Lakes, Lake Superior, Lake Michigan?
Yeah, so beaver wetlands are sometimes referred to as like the Brita filters of the landscape. So when you run agricultural runoff through them, when you have ash from fire running through them, they sequester that in the soil. There's unique biogeochemistry going on in the sediments and in the water itself that can help remove things like nitrates and phosphates from your water. And so if you have enough beaver dams on the tributary streams that run into the Great Lakes, you can be delivering less of these pollutants to the Great Lakes. And that matters for things like algal blooms. When you have them on streams that are maybe not as directly connected to the Great Lakes, but that can connect during stormwater events, that's also a way to help keep excess sediment out of the Great Lakes systems.
All right, thank you. With the overall benefits of change, we're seeing it seems that beavers are in many ways are the answer to a lot of our climate resilience questions and water quality issues. Um, I understand that you recently got a National Science Foundation grant, which congratulations, Yahoo, for that. Could you tell us about how that worked, what that will shape out your new studies?
Yeah, absolutely. So our new grant from the National Science Foundation is to create a North American Beaver Knowledge Network, where we're going to be bringing people together from the different regions across North America to look critically at the state of their science, the state of their policies, and the state of what people want in their landscapes, figure out where they align, where they don't align, and then bring all the regions together so that we can try to figure out, like, do we need another trout and beaver study? Yes or no? Can we extrapolate from what we have? Do we need another nitrate study? Is it actually unique here in Michigan or Minnesota versus what we've already seen in North Carolina or South Carolina? And so the goal of that is to stop duplicating the same studies over and over when it's not needed, and to be really targeted with getting the data and the information we need to make smart policies so that we don't miss the boat on working with beavers for climate change.
That sounds like a fantastic project. Congratulations on putting that together, and I wish you the best of luck. We'll probably have that as a next webinar as it develops.